Hello everyone, welcome to the class of Discrete Mathematical Structures 18CS36. Today, I'll be teaching a topic in Module 1, Fundamentals of Logic, and the topic name is Methods of Proofs and Disproofs. Myself, Dr. Madhura, Assistant Professor, Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. The methods of proof and the methods of disproof. Suppose P conditional Q is given for us, P implication Q, where P and Q are simple or compound propositions. The process of establishing that the condition is true by using the laws of logic or using the rules, etc., constitutes a proof of the conditional. So given a conditional for us, where P and Q are the simple or compound propositions, we establish the conditional is true by using some of the laws of logic, what we learned in the previous classes, or using any of the rules of inferences. And if we are able to prove the conditional is true, this gives us the proof of the conditional. Suppose the process of establishing that the proposition is false constitutes a disproof. So if we prove the conditional is true, it is the proof of the conditional. If we prove that the given implication is false, then it is the disproof of the conditional. First method. So there are different methods here in the methods of proof and disproof. We'll learn one by one. Direct method. The direct method of proving a conditional P implication Q has the following lines of argument. We talk about different ways of performing here. First one being the hypothesis, second one analysis, and thirdly the conclusion. So hypothesis, first we assume that P is true. And in the analysis step, we going to start with hypothesis. That is, we assume P is true and we employ the rules or the laws of logic or other known facts and infer that and try to arrive at Q is true. So that the conclusion will be P conditional Q is true. So there are three stages of proving in the direct method. One is the hypothesis, analysis, and the conclusion. So in the hypothesis, we first assume P is true. And keeping this P as true, we employ the rules of inferences or laws of logic or other known facts what we learned in the previous classes in logic. And we try to arrive at Q is true. So suppose we arrive at Q is true, then we will be able to say that P conditional Q is true. Recalling the implication 1, 1. True means the truth value is 1. So assuming P is true, its truth value will be 1. So Q cannot be 0. If this is 0, this becomes 1, 0. 1, 0 will give us 0 in the conditional. So we have to arrive at Q also is true. If we arrive at that, then we can conclude P conditional Q is true. Second method, indirect proof. We are familiar that the conditional P implication Q and its contrapositive negation Q implication negation P are logically equivalent to each other. We have already spoken about the contrapositive in the previous classes. So P conditional Q and negation Q conditional negation P are logically equivalent to each other. Keeping that in mind, in some situations, given a conditional which is of the form P implication Q, a proof of negation Q conditional negation P will be easier for us. So proving the contrapositive becomes easy in some of the situations. So this gives us the indirect proof for us. So on the basis of this proof, we conclude that P conditional Q is true. So indirectly, we will be proving the resultant using the contrapositive concept. So that gives us the indirect proof. Thirdly, proof by the method of contradiction. The indirect method of proof is equivalent to the proof by contradiction. The lines of argument in this method of proof of the statement P conditional Q are as follows. So again, the hypothesis, analysis, and the conclusion is considered. So in the hypothesis, we assume that P conditional Q is false. If P conditional Q has to be false, then P must be true and Q must be false. 1 0 implies a 0. So that is the reason P conditional Q is already concluded as false, means P should be true and Q should be false. This is our hypothesis. Then in the analysis, assuming Q is false and employing the rules or the laws of logic or other known facts, we have to infer that P is false. So we start with Q is false and apply some of the rules or the inferences what we are familiar with and try to arrive at P is false. When we arrive at P is false, this contradicts the assumption which is made in the hypothesis that P is true. So this is going to contradict the assumption what we have already made it in the hypothesis step that P is true. And hence we can conclude that because of the contradiction, we are going to infer that P conditional Q is true. So we proved the resulted by the method of contradiction. We arrive at a contradiction that P is false. This becomes a contradiction what we have already assumed in the hypothesis step that P is true. So due to contradiction, we will be able to infer that P conditional Q is true. Next, proof by exhaustion. We know that a proposition of the form for every x belonging to the universe S, P of x is true for every x in S. If S consists of only a limited number of elements, we can prove that the statement for every x belonging to S, P of x is true by considering P of A for each A in S. By considering P of A for each A in S and verifying that P of A is true in each case. So we have to prove for every element x belonging to the universe, we have to arrive at P of x is true. Suppose A is the element, then P of A is true, and in each case this should be true. So this gives us the proof by exhaustion. Such a method of proof is called the method of exhaustion. Next is proof by existence. We know that a proposition of the form for some x belonging to the universe S, P of x is true if any one element A in the universe is such that P of A is true is exhibited. So suppose for some x belonging to the universe, if we prove that the statement P of x is true, then it is proved that we are doing the proof by existence. So we take that element here considered as A. So for some A belonging to the S, we arrive at P of A is true. This should be exhibited. This is proof by existence. The best way to prove a proposition of the form for some x belonging to S, P of x is to find one A belonging to the universe S such that P of A is true. So we will try to find one such element A belonging to the universe such that P of A should be true. This is for some x belonging to the universe. So that is why we take one of the element, say A, we find that element from the universe denoted by A and prove the resultant P of A is true. So this is proof by existence for us. Next we have disproofs. There are two disproofs what we consider here. So disproof by contradiction. Suppose we wish to disprove a proposition P implication Q. So we want to disprove the given conditional. Then for this, let us assume first P is true and Q is true and end up with a contradiction. So when P is true, Q is true, and we try to end up with a contradiction, then let us assume P is true and Q is true and try to arrive at a contradiction in the method of disproof by contradiction. Hence, we will be able to conclude P conditional Q is false. So this method of disproving P conditional Q is called disproof by contradiction. So if I have taken P is true and Q is true, then P conditional Q must also be true. So we will be arriving at the contradiction part, and hence we will be able to conclude P conditional Q is false, which is known as the disproof by contradiction. We are not able to prove the resultant, so it is a disproof for us. So disproof by contradiction. Next is the disproof by counterexample. We can disprove a proposition involving the universal quantifier is to find one value for x for which the proposition is false. So we will be finding one such example from the universe, picking up a value, picking up an element from the universe and prove that the proposition is false. So this method of disproof is called disproof by counterexample. So we give a particular example and we prove the resultant is false or the proposition is false. So a particular case where the proposition is false is called a counterexample for the same. So these are the methods that we have in the direct proof, indirect proof, proof by contradiction, proof by exhaustion, proof by existence, and the two disproofs what we saw, disproof by contradiction and the disproof by counterexample. So we will do problems on the same. Problems on methods of proof and disproof. First question, I will take up a question on the direct proof. So first question, give a direct proof for each of the following. Give a direct proof for each of the following. First sub question in that. For all integers k and l, for all integers k and l, if k and l are both even, then k plus l is even. Second sub part of the question. For all integers k and l, if k and l are both even, then k into l is even. So this is a direct method for us. So we have to prove by direct method, right? So we take two integers k and l and we assume first both these are even. And since it belongs to a set of all integers, the universe here is a set of all integers, right? We can write down k as 2 into m and l as 2 into n, where both m and n belongs to the set of integers. Then we perform k plus l and k into l, check whether they both are even. If both are even, then we have proved the given two conditions by the direct proof, right? So let us see the solution. Take any two integers, k and l, and assume both k and l are even. Both k and l are even. Then k can be written as 2 into m, l can be written as 2 into n for m and n belonging to the set of integers, that is z. Now for the first case, we have to prove that k plus l is even, and for the second case, we have to prove k into l is even. So let us perform one by one. So we check for the first one that k plus l will be 2m plus 2n, or this can be written as 2 times of n plus n. 2 times of m plus n 2 times of m plus n is an integer which is divisible by 2. Which is divisible by 2. So this is an even number. Similarly, when I perform k into L, we have 2m into 2n. This is 4 into mn. 4 into mn is also an integer divisible by 2. So this is also even for us. So thus we can conclude k plus L and k into L are both even. And we have proved for some arbitrary integers k and L. This is true for any arbitrary integer k and L, and in view of the rule of generalization, universal rule of generalization, the proof is true for every for every integer k and L. So we'll conclude the same thing. Since k and L are arbitrary integers, since k and L are arbitrary integers, comma, in view of rule of universal generalization, the proof is complete. So this is the way we prove the direct proof. We give the direct proof for any particular propositions given for us. So if you can observe here, we did not in particular call an expression as P and Q, and we did, but it is indirectly the same thing what we had to actually do for the direct proof. What is the hypothesis, analysis and conclusion? We'll just recall once. So firstly, we will be assuming P is true in the hypothesis. In the analysis, inferring some rules or laws of logic or some direct methods, what we did in this problem, we try to infer that Q is also true. Then we will be able to conclude P conditional Q is true. So here, how do I read the P conditional Q? If K and L are both even, then K plus L is even. So in the hypothesis, I have to assume P and Q. Let P be K and L are even. Q be K plus L is even. Similarly, if K and L are both even as concluded as P, then K into L is even can be considered as Q. So we have proved the required result in that P conditional Q is true. Right? So this is how we do a problem for a direct proof. Second question. Provide a proof by contradiction. Provide a proof by contradiction of the following statement. For every integer n, comma, if n square is odd, If n square is odd, then n is odd. So this is the given statement for us. For this statement, we have to prove the resultant by contradiction. We have to prove it. Proof by contradiction. Correct? So let us recall what is the proof by contradiction. What is the method that we have learned in the theory about proof by contradiction. So there are three steps: hypothesis, analysis, and conclusion. So there are three steps in proof by contradiction: the hypothesis, analysis, and the conclusion. In hypothesis, we assume P conditional Q is false. P implication Q is false. That is, P is true and Q is false. And in the analysis, we employ the rules of inference or the laws of logic, and we infer that, or we arrive at P is false. P is false, which contradicts the assumption what we made in the hypothesis. So that is the reason conclusion will be proof by contradiction. P conditional Q will be true. So that is how we do the method in proof by contradiction. So let us implicate the same thing and do the problem. Solution. Solution. We have proof by contradiction to do. So let us assume P equal to, let us assume P equal to n square is odd, and let us assume Q as n is odd, right? If P, then Q form. So that is the conditional we have here, no? So let us assume P be such that, let us assume P be such that n square is odd, and let us assume Q such that n is odd. N is odd. So given statement reads the form P conditional Q. P implication Q form. Now according to the proof by contradiction, we have to assume P conditional. In the hypothesis, we take no P conditional Q is false. In the hypothesis, we assume that P conditional Q is false. Then P is true, P is true, and Q is false. P is true and Q is false. Now in the, this is the hypothesis step test. Then in the analysis, we have to consider Q is false. We have to consider Q is false and try to arrive at the contradiction, that is P is false. So let us consider Q is false. Q is false. So this implies Q stands for n is odd. So Q is false means n is even. So n is even. So if n is even, then n can be written as 2 into say k, where k belongs to the set of integers. K belongs to set of integers. So therefore, what happens to n square? N square will be 2k the whole square, which is 4k square. 4k square is also an even integer. So we arrived at, if you observe, P is false. What was P? P we had assumed that n square is odd. Now we have arrived at n square is even. N square is even. So we can conclude that P is false. So this is a contradiction to the assumption that P is true. We have already made the assumption. I will just underline the assumption here. We assume P conditional Q is false, then P is true and Q is false. Correct? 1, 0 gives us 0. So that is why P conditional Q is false means P has to be true and Q has to be false. So this is the assumption what we had made, and this assumption, according to the assumption, P was supposed to be true, but we have arrived at P is false. So this contradicts the assumption that P is true. We will write the same thing. This contradicts the assumption that P is true. So therefore, by the method of proof by contradiction, by the method of proof by contradiction, P conditional Q is true. And that is, according to the given data, it means that if n square is odd, then n is odd. If n square is odd, then n is odd. So this is how we do a problem by proof by contradiction. Let us do the third problem. Third one. Give a direct proof, an indirect proof, and proof by contradiction. We'll put the numberings as 1, 2, 3 sub-numberings. So give a direct proof, an indirect proof, and thirdly, proof by contradiction, proof by contradiction for the following statement. For the following statement, we'll write down the statement in quotes. If n is an odd integer, if n is an odd integer, comma, then n plus 9 is an even integer. N plus 9 is an even integer. So for the given statement, we have to give a direct proof, an indirect proof, and the proof by contradiction. So we are trying to do 3 different proofs here and prove the required resultant. So let's see the solution. The first one is by direct proof. Let us assume that n is an integer, n is an odd integer. Direct proof means, for direct proof, we need not write down p, q and all. Okay, directly we will be able to prove the resultant. So that is the reason I usually don't write down. N is an odd integer is what we have to take the proposition as p, and q we should take it as n plus 9 is an even integer. So direct proof says that it is p conditional q. Given question is of the form p conditional q. In the direct proof also we have 3 steps: hypothesis, analysis, and the conclusion. In the hypothesis we assume p is true. In the analysis we try to arrive at q is true, such that the conclusion will be p conditional q is true. So that's the direct proof for us. Okay. So let us do the direct proof. Assume that n is an odd integer. N is an odd integer. So we assume p is true and try to infer at q is true. So I have to now take n is an odd integer. So if n is an odd integer, this gives us n is equal to say 2k plus 1. Any odd number can be represented in the form 2k plus 1, where k belongs to the set of integers here. So what will be n plus 9 then? I have to obtain the resultant for n plus 9 and prove that n plus 9 is an even integer. So let us perform n plus 9, which will give us 2k plus 1 plus 9, which is same as writing 2k plus 10, or this can be written as 2 times of k plus 5. 2 times of k plus 5 is an even number. It is multiplied by 2, so this is an even integer. So thus can we conclude that n plus 9 is even. N plus 9 is even. So which gives us the direct proof for the given statement. So we started with P is true, we arrived at Q is true, and thus P conditional Q is true. P conditional Q means if n is an odd integer, then n plus 9 is an even integer. So that is the direct proof for us. Now the second one. Second one is to prove by indirect proof. We have to prove the given statement is true by indirect proof. So let us now recall what is that indirect proof for us. Indirect proof. Indirect proof is same as saying it is proof by contrapositive. So we will be proving the statement by contrapositive. That is negation Q conditional negation P is true. So that's the indirect proof for us or the contrapositive proof for us. So we are now actually doing the indirect proof. Indirect proof, this is one and the same as writing proof by contrapositive. Proof by contrapositive. Both these are one and the same to understand. Okay. So let us do the proof by contrapositive. So let us assume P as n is odd and Q be the expression or the statement given by n plus 9 is even. N plus 9 is even. So given statement reads the form P conditional Q. So what is the contrapositive of this? So its contrapositive is of the form negation Q conditional negation P. Negation Q conditional negation P. And remember, this is what we are supposed to prove. We are supposed to prove the contrapositive. So that gives us the indirect proof. So this is what we have to prove now. So let us prove the contrapositive. So to do this, we have to now assume negation Q is true and we have to try to arrive at negation P is true. Right? So let us assume or suppose that negation Q is true. So what does this imply? Negation Q is true means Q is denoted by the statement n plus 9 is even. So negation Q means what? N plus 9 is odd. So we have n plus 9 is odd. N plus 9 is odd. Then how can we write down that odd integer? So n plus 9 can be written as 2k plus 1. Any odd integer is always represented in the form 2k plus 1, where k belongs to set of integers z. So what is n from this? We will just rearrange the terms and write down what is n from this. So we are getting n is equal to 2k plus 1 minus 9. Plus 1 minus 9 can be written as minus 8. So we have n equal to 2k minus 8. And we can write down this n is equal to 2k minus 8 taking 2 common. We can write it down as k minus 4. 2 times of k minus 4 is representing an even integer. So did I arrive at n is even? We arrived at n is even, no? So if I am arriving at n is even, this is one and the same as saying negation P is true. P stands for n is odd. So negation P means n is even. So I have arrived at n is even, no? So it is one and the same as saying that. Negation P is true. Negation P is true. So just for your observation, I'm underlining. So see, we started with the condition that negation Q is true, and we have arrived at negation P is true. We started with negation Q is true and we have arrived at negation P is true. So we have proved the contrapositive. So we have proved the contrapositive, which is one and the same as giving the proof by indirect method. So we can just conclude this proves the contrapositive. This proves the contrapositive for us. So this was the second part of the problem for us. Now, before we move on to the third one, let's see what is the third part of the question. We have to prove the result and prove the statement given by the proof of contradiction. So proof by contradiction we have to do. So last problem we have checked how to do proof by contradiction. Let us see the same thing now. Proof by contradiction. This is the third part for us. Proof by contradiction. So let us assume P and Q. Let P be the statement n is odd and Q be the statement n plus 9 is even. P be the statement n is odd and Q be the statement n plus 9 is even. So that is what we had here, no? N is an odd integer, n plus 9 is an even integer. So given statement reads the form. Given statement reads the form P conditional Q. P conditional Q. So what does the proof by contradiction say? We have to assume that P conditional Q is false, which will give us P is true and Q is false. So starting with Q being false, we have to arrive at a contradiction that P is also false. So if we arrive at the contradiction part, assuming Q is false, if we arrive at P is false, then we have proved by the contradiction method. So let us see how to do that. So very firstly, assume that P conditional Q is false. That is, P is true and Q is false. So remember, when can a conditional be false? A conditional can be false only when 1 0 form. When it is of the form 1 0, the conditional will be 0. So 1 0, if it has to be, means P should be true, Q should be false. 1 means true, false means 0. So P should be true and Q is false. Now we will consider Q is false and try to arrive at the contradiction. Consider Q is false. So this implies, what is the Q we have taken? N plus 9 is even we have taken. Means I have to take Q is false, means I have to assume N plus 9 is odd. So N plus 9 is odd, I have to start with. If N plus 9 is odd, then N plus 9 can be represented as 2k plus 1, where k belongs to set of integers. So N plus 9 is equal to odd integer can be represented as 2k plus 1. So this gives us N is equal to 2k plus 1 minus 9, or N is equal to 2k minus 8, which is 2 times of k minus 4, which represents a even integer. So we have arrived at N is even. N is even. But what is our P? P is N is odd. N is odd. But we have arrived at the contradiction of it. So this contradicts the part that we have already taken P is true. So according to our assumption, this is a contradiction. So this contradicts the assumption the assumption that n is odd. We have taken the assumption here, no? I'll just underline that for you and show. So what did we assume? We assume that P conditional Q is false, and this is going to imply P is true and Q is false for us. So starting with Q equal to false, we arrived at P is false. So n is even means this implies for us P is false. But according to our assumption, P should have been true. So this is a contradiction to the assumption what we made, and hence we can conclude that P conditional Q is true. We can assume, or we can come to the conclusion finally that P conditional Q is true. Means given conditional which says that if n is an odd integer, then n plus 9 is an even integer. Right? If P, then Q. This is true. So this is how, in this problem, we saw that for the given statement, we were able to give a direct proof, indirect proof, and the proof by contradiction also. Let us take up the next question. Fourth one. Prove that every even integer n, with 2 less than or equal to n less than or equal to 26 can be written as a sum of at most 3 perfect squares. So every even integer n, where n lies between 2 to 26, can be written as a sum of at most 3 perfect squares. So let us prove the resultant. If you observe the question, there is nowhere mentioned which method we have to use and do. But when we see the word every, for every even integer we have to prove between 2 to 26. The even integers between 2 to 26 are 2, 4, 6, 8, etc. up to 26. Correct? So since we have to prove the resultant for every even integer lying in this range, it is the proof by exhaustion. So let us recall what is the proof by exhaustion. It says that for every x belonging to the universe S, P of x is true. We have to prove the statement. Here the statement is nothing but it is every even integer is written as a sum of at most 3 perfect squares. That is the statement P of x for S. And for every x belonging to the universe S, we have to prove that P of x is true. So we take the element A in S and we verify for every element P of A is true. We take any element A in the set in the universe S, and we prove the resultant is true for every P of A. Okay, so let us do the solution now. Solution. So very firstly, let us assume the universe S and write down the elements. We have S taking the elements from 2 to 26. We have to do it for all even integers. So S consists of 2, 4, 6, 8, etc. up to 26. This is the universe S for us. And let us assume P of x is such that x is a sum of at most 3 perfect squares. X is a sum of at most 3 perfect squares. So this is our statement P of x. We have to prove the statement is true for every element from the universe S. So we should be able to express each of the elements 2, 4, 6, 8, etc. Each one of this we should be able to express as a sum of at most 3 perfect squares. Okay, so let us just write down what is to be proved. To prove that the statement for every x belonging to the universe S, P of x is true. This is nothing but proof by exhaustion. Proof by exhaustion. So we will do it for one by one. So we have writing down for 2, we can express 2 as 1 square plus 1 square. So sum of 2 perfect squares we are doing for 1 for the number 2. Next, what about 4? 4 we can express as 2 square, no? Then 6. 6 can be expressed as 2 square plus 1 square plus 1 square. So we saw it is expressed as a sum of 3 perfect squares. Then 8. 8 can be written as 2 square plus 2 square. Then we have 10. 10. 10 can be written as 3 square plus 1 square. 9 plus 1. Then we have 12. All even integers we have to do. So 12 can be represented as 2 square plus 2 square plus 2 square. See to it that you are able to express the sum of at most 3 perfect squares. Okay. Then we have 14. 14 can be represented as 3 square is 9 plus 2 square plus 1 square. Correct, no? 9 plus 4 plus 1, which is 14. Then we have 16. 16 can be represented as 4 square. Then we have 18, which can be written as 4 square plus 1 square plus 1 square. Then we have 20. This can be represented as 4 square plus 2 square. 4 square is 16 plus 2 square is 4. 16 plus 4, 20. Next we have 22. 22 can be written as 3 square plus 3 square, that is 9 plus 9, 18 plus 4, so 2 square. Then we have 24, which can be written as 4 square plus 2 square plus 2 square. 16 plus 4, which is 24. Finally, 26 can be written as 5 square, 25 plus 1 square. It is just a small trial and error. Every integer, every even integer between 2 to 26 can be expressed as a sum of at most 3 perfect squares. Maximum 3 perfect squares we are taking here. So it is a sum of at most 3 perfect squares. So we have verified for every element A belonging to the set S. So we can conclude, therefore, each x in S is a sum of at most 3 perfect squares. So this is proof by exhaustion for us. Now I would like to take up one problem on disproof. So disproof, we will do one problem. Disprove the statement. Disprove the statement. You can write on the statement in quotes. The sum of two odd integers. The sum of two odd integers is an odd integer. Is an odd integer. So we need to disprove this statement. So orally when we observe for any particular value, obviously this is a false statement, no? If I take two odd numbers, two odd integers and take up their sum, it is usually an even integer. So that is what we have to, it is given it is an odd integer. So that is the reason we have to disprove this statement. So let us see the solution. This is disproof by contradiction. We are proving the result or we are disproving the statement by disproof by contradiction method. So let us assume P and Q first. Let P be the condition. A and B are odd integers. A and B are odd integers. I take two integers which are denoted by A and B. And let us assume Q be the statement that sum. Sum is A plus B. A plus B is an odd integer. See, very firstly, when you see the question, it is actually not in the form of a condition. It is actually not in the form of a condition, but we can put it in the form of a conditional and then apply the disproof by contradiction. How can we write down the given statement in the form of a conditional is, if there are two odd integers, then their sum is an odd integer. So if then form you are considering. If there are two odd integers, then their sum is odd integer. So that is how we can write down in the form of if then. So that's the reason we took it in the form PQ. So A and B are odd integers. A plus B is an odd integer. If P, then Q. Now the proposition to be disproved. The proposition to be disproved is P conditional Q. P conditional Q. So let us assume P is true and Q is true. Let us assume P is true and Q is true. So what is the statement P being true? When I say P is true, I have to take A and B both as odd integers. So I'll take A as say 2k plus 1 and B is represented as say 2k2 plus 1. Then we have A plus B. Q is true, we have to take note, that is A plus B is also 2k3 plus 1. Say odd integer. We are representing both of them in the form of odd representation, odd integer representation. Okay, so we have A equal to 2k1 plus 1, B equal to 2k2 plus 1. I'll assume this as expressions 1, equation 1. And we have Q is true, that is A plus B is equal to odd integer. So 2k3 plus 1. Let us assume this as equation 2, where k1, k2, k3 all belongs to set of integers. All belong to set of integers. Now what is that? From 1 we have, from 1 let us add A and B. Okay, from equation 1 we are adding A and B. What do we get? 2k1 plus 1 plus 2k2 plus 1. So this is same as writing 2k1 plus 2k2 plus 2. We have 1 plus 1 which is equal to 2. So we have 2 common in all of them. So this gives us 2 times of k1 plus k2 plus 1. k1 plus k2 plus 1. So is this implying to me that A plus B is even? This is representing an even integer, no? So we have concluded that A plus B is even. But according to our assumption from equation 2, our equation 2 is A plus B is an odd integer, no? We assumed here that A plus B is an odd integer. So from 2, this is a contradiction. This is a contradiction. From 2, it is an odd representation. From the arrival, we have A plus B is even. So this contradicts the assumption made in equation 2. So therefore, P conditional Q is false. We started with what? We started with P conditional Q is true. So P is true, Q is true, we started. So now we have arrived at P conditional Q is false. So this proves or this disproves the given statement. So we'll just write down which disproves the given statement. So this is how we can work out a problem in disproofs also. So these were the problems on methods of proofs and disproof. Hope you have followed these problems. Thank you for watching.